Tonight, we're going to talk about something that might sound impossible. The Big Bang wasn't the beginning. According to Sir Roger Penrose, a Nobel Prize-winning physicist, the universe you're living in right now is just one chapter in an infinite story, an endless cycle of death and rebirth, stretching backward and forward through eternity. And the evidence, he claims, is written in the oldest light we can observe. By the end of tonight, you're going to understand why the most powerful telescope ever built keeps finding things that shouldn't exist, and why those discoveries might be pointing us toward a cosmos far stranger than anyone imagined. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In 2020, Sir Roger Penrose received the Nobel Prize in Physics, not for his cyclic universe theory, for proving that black holes form naturally from Einstein's equations. The Nobel Committee honored decades of rigorous mathematical work, demonstrating that general relativity leads inevitably to singularities, points where space and time break down completely. But Penrose didn't stop there. He kept thinking about those singularities, about what they mean, about what happens when you push physics to its absolute limits. And somewhere in that thinking, he developed an idea so audacious that most physicists dismissed it as impossible. Conformal cyclic cosmology. The universe, Penrose argues, doesn't begin and end once. It cycles, forever. Each universe expands until all matter decays into pure energy, until everything is just photons racing through an empty void. And in that state, something extraordinary happens. Time loses meaning. Scale loses meaning. The infinite future of one universe becomes indistinguishable from the Big Bang of the next. Think about that for a moment. The end becomes the beginning. Our Big Bang wasn't the moment of creation. It was a transition, an explosive handoff from a previous universe that had expanded itself into oblivion. The theory is built on something called conformal geometry, a mathematical framework where you can stretch and squash space-time while preserving certain relationships between angles and shapes. Penrose realized that if you take the infinitely stretched out end of an old universe and apply the right conformal transformation, it looks exactly like the compressed, hot beginning of a new one. The two states, separated by an eternity of time, become mathematically equivalent. You can map one onto the other. This isn't science fiction. It's rigorous mathematics developed by one of the world's leading mathematical physicists. But mathematics alone doesn't make something true. You need evidence. You need observations that match the theory's predictions. And that's where things get interesting. Because Penrose claims he's found exactly that evidence. In 2010, Penrose and his colleague Vahe Gurzadian published a paper claiming they'd discovered mysterious circular patterns in the cosmic microwave background. The cosmic microwave background is the afterglow of the Big Bang, the oldest light in the universe. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This radiation has been traveling through space for more than 13 billion years. We detect it today as microwave radiation coming from every direction in the sky. It's remarkably uniform, with temperature variations of only about 1 part in 100,000. But within that uniformity, there are tiny fluctuations, hot spots and cold spots that represent the seeds of all the galaxies and structures we see today. Penrose and Gurzadian claimed they found something unusual in this data, concentric circles, rings of slightly lower temperature variation arranged in circular patterns across the sky. These weren't random. They appeared far more frequently than statistical chance would predict. Penrose had a specific explanation for these patterns. He called them Hawking points. In Penrose's cyclic cosmology, the previous universe was dominated by supermassive black holes in its final stages. As that universe expanded toward infinity, these black holes slowly evaporated through a process called Hawking radiation. Stephen Hawking proved in 1974 that black holes aren't completely black. They emit faint radiation and gradually lose mass. For a supermassive black hole, this process takes an unimaginably long time, far longer than the current age of the universe. But in Penrose's model, the previous universe had all the time it needed. Eventually, every black hole evaporated completely. The radiation from this evaporation, Penrose argues, gets carried forward into the next universe. It shows up as a glowing disk in the cosmic microwave background, an imprint of a black hole from before our Big Bang. Each Hawking point represents the death of a supermassive black hole in the previous aeon. Penrose claimed these disks should appear roughly the size of the full moon in our sky. And that's what he found in the data from the Planck and WMAP satellites, hundreds of them. Statistical analysis suggested the probability of finding this many circular patterns by chance was less than 1 in 125. If true, this would be direct observational evidence of a universe before ours. Proof that the Big Bang wasn't the absolute beginning. But science doesn't work on single papers, no matter how distinguished the author. Other physicists immediately began checking Penrose's work. Within weeks, multiple research groups published rebuttals. They created simulated cosmic microwave background maps using the standard model of cosmology, with no previous universe, no cyclic structure, nothing exotic. And they found just as many circular patterns in their simulations as Penrose found in the real data. The circles, they argued, were statistical artifacts. If you look at enough random data, you'll find patterns that seem significant but actually mean nothing. It's called the look elsewhere effect. If you test enough hypotheses, one of them will appear to be confirmed purely by chance. Penrose's analysis, critics claimed, suffered from this problem. He'd tested thousands of possible circle centers, effectively running thousands of different statistical tests. Find enough circles that seem unusual, and you can claim success, even if the underlying data is completely random. Penrose pushed back. He argued that the critics misunderstood his methodology, that the circles he found were qualitatively different from random noise. Papers went back and forth through 2011 and 2012. The debate never fully resolved. Most physicists concluded the Hawking points probably weren't real. The evidence wasn't strong enough to overturn the standard Big Bang model. But Penrose didn't give up. In 2018, Penrose published new evidence. This time, instead of looking for circles of uniform temperature, he looked for hotspots, unusually warm patches in the cosmic microwave background where the temperature gradient was much steeper than anywhere else. These hotspots, he argued, were another signature of Hawking radiation from the previous universe. The electromagnetic energy released during black hole evaporation would concentrate into specific points in the next universe's cosmic microwave background. He analyzed data from the Planck satellite and compared temperature gradients in the real universe to temperature gradients in 1,000 simulated universes generated by standard cosmology models. The result was striking. in and around small hotspots. Not a single simulated map had higher temperature gradients than the real cosmos. The temperature variations in real observations were about an order of magnitude higher than what standard models predicted. This time, the claim was harder to dismiss. Temperature gradients are a different kind of signal than circular patterns. They're less susceptible to the look elsewhere effect. But still, most cosmologists remain skeptical. The standard model of cosmology has been tested countless times through countless different observations. It explains the cosmic microwave background, the abundances of light elements, the large-scale structure of the universe, the expansion rate, all of it fitting together into a coherent picture. Overthrowing that model requires extraordinary evidence. Penrose's hotspots, while intriguing, weren't enough. And then the James Webb Space Telescope started making observations. Webb launched on Christmas Day, 2021. It's the most powerful space telescope ever built, with a mirror over 21 feet across, or 6.5 meters, and instruments sensitive to infrared light. This combination allows it to see farther back in time than any previous telescope. Light from distant galaxies gets stretched by the expansion of the universe. The farther away something is, the more its light shifts toward redder wavelengths. Webb's infrared sensitivity means it can detect light from galaxies so distant that their visible light has been stretched all the way into the infrared. Almost immediately after it began science operations in July 2022, Webb started finding things nobody expected. Galaxies. Massive, bright, fully formed galaxies in the first few 100 million years after the Big Bang. Places and times where, according to standard models, such galaxies shouldn't exist yet. One of Webb's first targets was a region near the Big Dipper. The telescope detected faint lights that had traveled for over 13 billion years. These objects were born just 500 million years after the Big Bang, and they were enormous, already rivaling the Milky Way in size. This shouldn't be possible, according to current cosmological models. In the standard picture, the early universe was filled with dark matter that gradually collapsed into halos under gravity. Normal matter fell into these halos and slowly formed the first stars and galaxies. This process takes time. A lot of time. The first galaxies should have been small, perhaps a few million solar masses. Over billions of years, they merged and grew into the massive structures we see today. But Webb was seeing massive galaxies that existed when the universe was barely 500 million years old. There simply hadn't been enough time for them to grow so large. Astronomers started calling them universe breakers, because they appeared to break our understanding of how the universe evolved. The discoveries kept coming. Webb identified galaxy after galaxy, containing far more stars than expected for such an early epoch. In February 2023, researchers published findings about 6 galaxies that appeared to be between 10 and 100 times more massive than theoretical models predicted. If confirmed, these galaxies would require rethinking fundamental aspects of cosmology. Either dark matter behaves differently than we thought, or galaxy formation happened much faster than our models allow, or something else entirely is going on. One proposed explanation involved measurement errors. Maybe these galaxies aren't as massive as they appear. Maybe dust is affecting the observations. Or maybe some of the light is coming from active black holes rather than stars, making the galaxies look bigger than they really are. By late 2023 and into 2024, follow-up observations began addressing some of these concerns. Some of the alleged universe breakers turned out to be less massive than initially thought. Others were confirmed as genuinely puzzling. A study comparing Webb's observations with older Hubble data suggested the problem might not be as severe as it first appeared. The researchers looked at an era where both telescopes could observe galaxies between roughly 450 million and 750 million years after the Big Bang. If there really were 10 times more massive galaxies than expected in the early universe, Hubble should have seen 10 times more galaxies too. It didn't. This suggested that at least some of the Webb discoveries might be explained within standard cosmology, perhaps with tweaks to how efficiently gas converts into stars. But not all the anomalies disappeared. In January 2026, Webb confirmed the discovery of MOME Z14, a galaxy visible just 280 million years after the Big Bang. This is now the most distant galaxy ever confirmed. Light from this galaxy has been traveling toward us for more than 13.5 billion years. When that light began its journey, the universe was only 2% of its current age. The galaxy is 1,600 light-years across and remarkably luminous. Spectroscopic analysis revealed strong ionized gas emissions, including hydrogen and oxygen. Finding oxygen is particularly surprising. Oxygen is created inside stars when helium fuses together. It takes multiple generations of stars to produce significant amounts of oxygen. A star forms, lives, and then dies in a supernova, scattering oxygen into space. That oxygen gets incorporated into new stars, which eventually also die and scatter more oxygen. This cycle repeats until there's enough oxygen to detect in a galaxy's spectrum. All of this takes time. But MOME Z14 existed only 280 million years after the Big Bang. There wasn't enough time for multiple generations of stars. Yet the oxygen is there. Researchers noted that some ancient stars in the Milky Way show unusual nitrogen enrichment, and Webb is seeing similar nitrogen signatures in these early galaxies. It's as if the early universe was somehow producing heavy elements faster than it should have been possible. This rapid chemical enrichment is one of the most profound mysteries Webb has uncovered. In the standard model, creating heavy elements requires a specific sequence of events. The first stars, called population 3 stars, were made purely of hydrogen and helium. They lived fast, died young, and exploded as supernovae, scattering the first heavy elements into space. Those elements got incorporated into the next generation of stars, population 2. These stars created even more heavy elements and scattered them when they died. Only after multiple generations do you get population 1 stars, like our Sun, which contain enough heavy elements to form rocky planets. This process takes hundreds of millions of years, possibly over 1 billion. Yet Webb is finding significant amounts of oxygen, carbon, and nitrogen in galaxies that existed only 200 to 300 million years after the Big Bang. Something accelerated this process. Either the first stars formed much earlier than we thought, or they produced heavy elements far more efficiently than our models predict, or there's a completely different mechanism at work that we haven't considered. Let's dig deeper into this chemical enrichment problem. The process by which stars create heavy elements is called nucleosynthesis. Inside the cores of stars, hydrogen fuses into helium. In more massive stars, the process continues. Helium fusing into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each fusion reaction releases energy that keeps the star from collapsing under its own gravity. But iron is the end of the line. Fusing iron requires more energy than it releases. When a massive star's core turns to iron, fusion stops. Without the outward pressure from fusion, gravity wins. The core collapses catastrophically in less than a second. The outer layers rebound in a supernova explosion. This explosion creates extreme conditions where elements heavier than iron can form. The rapid capture of neutrons, called the R process, creates gold, platinum, uranium, and other heavy elements. The supernova also disperses all these elements into the surrounding space. This enriched gas eventually becomes part of the next generation of stars and planets. This is how the periodic table gets built, element by element, generation by generation. But it takes time. A massive star might live for only a few million years before going supernova. But you need enough time for that star to form, for it to evolve through its life cycle, and for it to explode. Then you need time for the enriched gas to cool and condense into new stars. Multiple cycles of this process are required to build up significant concentrations of heavy elements. Standard models suggested this would take at least 500 million years, probably closer to 1 billion. Yet Webb is finding galaxies with substantial heavy element enrichment at 300 million years. How? One possibility is that the first stars were far more massive than we thought. If population 3 stars had masses of hundreds or even thousands of suns, they would have burned through their fuel in just a few million years. They would have produced vast quantities of heavy elements and dispersed them through powerful supernovae. This could accelerate the enrichment process. But there's a problem with this idea. Very massive stars are unstable. Theoretical models suggest stars above a certain mass, around 200 to 300 solar masses, become so luminous that radiation pressure blows them apart before they can finish forming. They simply can't exist, unless something about the early universe changed this limit. Maybe the lower metallicity of the first stars allowed them to be more massive. Maybe different cooling processes were at work. Another possibility is that some of the first stars collapsed directly into black holes without exploding. These failed supernovae wouldn't enrich the interstellar medium. But if only a fraction of massive stars fail to explode, that might actually help. The stars that do explode would be more effective at dispersing their heavy elements. Or perhaps there's a completely different source of heavy elements we haven't considered. Colliding neutron stars create enormous amounts of heavy elements through the R process. If neutron star mergers were more common in the early universe, they could contribute significantly to chemical enrichment. But this seems unlikely. Neutron stars form from supernova explosions. You need supernovae first, before you can have neutron star mergers. The mystery remains unsolved. Every explanation requires either changing our understanding of stellar evolution or invoking processes we haven't observed, or accepting that the early universe was fundamentally different in ways our models don't capture. And then, there's the Hubble tension. This is one of the biggest unsolved problems in cosmology right now. It has to do with how fast the universe is expanding. The expansion rate is called the Hubble constant. If you measure it using light from the cosmic microwave background, you get about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.26 million light-years, space expands by 67 kilometers every second. But if you measure the Hubble constant using observations of nearby stars and galaxies, you get a different answer. About 73 kilometers per second per megaparsec. That's a 9% difference. 9% might not sound like much, but in science, it's huge. Both measurements are extremely precise, with error bars much smaller than the gap between them. This shouldn't be happening. If our understanding of the universe is correct, both methods should give the same answer. For years, scientists hoped one of the measurements was wrong. Maybe there was some systematic error in how distances were calculated, or maybe dust was affecting observations in unexpected ways. The Hubble Space Telescope made the nearby measurements using pulsating stars called Cepheid variables. These stars change brightness at regular intervals, and the period of pulsation is directly related to their intrinsic luminosity. By measuring how bright they appear and comparing to how bright they actually are, you can calculate their distance. This technique is well established and has been refined over decades, but maybe, critics suggested, there was crowding. Maybe multiple stars were blending together at great distances, making the measurements less accurate. Then Webb started making its own measurements. Webb has 4 times the resolution of Hubble and roughly 10 times the sensitivity. It can see through dust, and clearly separate individual stars that Hubble could only see as blurry groups. If there were systematic errors in Hubble's measurements, Webb should reveal them. In late 2023 and through 2024, Webb observed the same Cepheid variables Hubble had measured. The results matched. Webb confirmed Hubble's measurements with remarkable precision. The local expansion rate really is about 73 kilometers per second per megaparsec. This means the discrepancy is real. It's not a measurement error. The universe really does seem to be expanding at different rates, depending on how you measure it. Or more precisely, the expansion rate you calculate depends on whether you use data from the early universe or the present-day universe. Some researchers proposed exotic physics to explain this. Maybe dark energy evolved over time. Maybe the cosmological constant isn't actually constant. Maybe there's early dark energy that existed briefly in the first moments after the Big Bang. These ideas could potentially reconcile the measurements, but they require adding new physics to our models. Other researchers had a different thought. What if the standard model itself is incomplete? What if something fundamental about how we understand the universe's history is wrong? This is where the story takes an even stranger turn. Some cosmologists have begun exploring a radical possibility. What if our universe isn't alone? What if it's one bubble in an infinite foam of universes? And what if these universes can interact? The multiverse isn't a new idea. It emerges naturally from certain interpretations of quantum mechanics and from inflationary cosmology. But usually, these other universes are thought to be completely separate, causally disconnected from ours. We can't see them. We can't touch them. They can't affect us. But what if that's wrong? What if during the inflationary epoch, the first fraction of a second after the Big Bang, our universe interacted with another universe? Maybe it collided with a neighboring bubble. Maybe it was absorbed into a larger parent universe. Maybe it split off from a previous universe in a way that left detectable traces. Mathematical models have been developed to explore these possibilities. Researchers simulate multiple universes interacting gravitationally, merging, exchanging energy. The results are fascinating. When 2 universe bubbles collide, the interaction creates ripples in space-time that propagate through both universes. These ripples could show up as anomalies in the cosmic microwave background, not Penrose's circular patterns, necessarily, but other kinds of patterns, asymmetries, features that can't be explained by single universe inflation. Some researchers claim they've found hints of such asymmetries in the cosmic microwave background data. A preferred direction in space, a slight temperature difference between one hemisphere of the sky and the other. These anomalies are subtle and contested, They could be real signals of multiverse interactions, or they could be instrumental effects or statistical flukes. But the possibility is intriguing. If our universe did interact with another universe during inflation, that interaction might have seeded our universe with more structure than standard inflation predicts. It might have created density fluctuations that led to faster galaxy formation. It might explain why we're seeing massive galaxies so early. The interaction could also affect the expansion rate. If our universe absorbed mass energy from another universe, or if the collision imparted momentum to our cosmic expansion, the expansion rate could be different from what single universe models predict. This wouldn't be the same as Penrose's cyclic cosmology. These are contemporary multiverse models based on inflation, not on conformal geometry. But they share something important with Penrose's idea. They both suggest that what we call the Big Bang might not have been the absolute beginning. It might have been a transition, a collision, an interaction with something that existed before. Now let's talk about what Webb found that might be the strangest discovery of all: the little red dots. When Webb first started observing the deep universe, astronomers noticed hundreds of peculiar objects in the images. Tiny red dots, compact and bright, appearing in regions of space corresponding to the first billion years after the Big Bang. These objects were completely unexpected. Nobody had seen anything quite like them before. At first, researchers thought they might be distant galaxies heavily obscured by dust. Dust absorbs blue and ultraviolet light, making galaxies appear redder. But the more they studied these objects, the weirder they got. The little red dots are extraordinarily compact, much smaller than typical galaxies. They're also incredibly bright for their size. If they were made purely of stars, they would be the densest galaxies in the universe, with stars packed so tightly together that the night sky on a planet in such a galaxy would be blazing with millions of nearby suns. But spectroscopic analysis revealed something even stranger. These objects show extreme emission lines, signatures of intensely hot gas being illuminated by something powerful. The spectra don't quite match star-forming galaxies. They don't quite match active galactic nuclei powered by supermassive black holes either. They're something in between, or something entirely different. For over 2 years, astronomers debated what the little red dots could be. Several theories emerged. One idea suggested they might be supermassive stars, objects with millions of times the mass of our Sun. These hypothetical stars would be short-lived, burning incredibly hot and bright before collapsing directly into black holes. They could explain the extreme brightness and the unusual spectral features. Another theory proposed they were young, black holes surrounded by dense cocoons of gas. As the black holes accreted matter, they would heat the surrounding gas to extreme temperatures, producing the observed emission. The gas cocoon would absorb and re-radiate the light, giving the objects their distinctive red appearance. In January 2026, a breakthrough came. Researchers from the University of Copenhagen published a study in Nature, identifying the little red dots as young black holes embedded in extremely dense clouds of ionized gas. These black holes are about 10 million solar masses, large but not yet supermassive. They're accreting matter voraciously, growing rapidly as they consume the gas around them. The radiation from this accretion heats the gas cocoon to temperatures of hundreds of thousands of degrees. This glowing envelope is what we're seeing. The reason they appear red is that the dense gas absorbs shorter wavelengths of light, ultraviolet and blue, but allows longer wavelengths, red and infrared, to escape. But here's the problem. These black holes shouldn't exist yet. A black hole with 10 million solar masses requires either a very long time to grow through accretion, or it needs to start from a much larger seed than we think is possible. In the standard picture, black holes form from dying massive stars. These stellar mass black holes might be 10 to 100 times the mass of the Sun, growing from 100 solar masses to 10 million solar masses through accretion takes hundreds of millions of years, possibly over 1 billion. But the little red dots exist when the universe is only a few 100 million years old. There wasn't enough time for them to grow so large through normal accretion. So where did they come from? One possibility is direct collapse black holes. Under very specific conditions in the early universe, a massive cloud of gas could collapse directly into a black hole without forming a star first. This would create a much larger seed, perhaps 10,000 or even 100,000 solar masses. Growing from 100,000 solar masses to 10 million solar masses is much faster, potentially achievable in the available time. But direct collapse requires very unusual conditions. The gas cloud needs to be pristine, with almost no heavy elements, and it needs to avoid fragmenting into smaller pieces that would form stars. Simulations suggest this might happen in rare regions of the early universe, where conditions were just right. Another possibility is even more exotic. What if some of these black holes are primordial, formed in the first moments after the Big Bang itself? If the early universe had density fluctuations large enough, regions of space could have collapsed directly into black holes when the universe was less than a second old. These primordial black holes would have had billions of years to grow before the little red dots were observed. This is speculative. We have no direct evidence for primordial black holes, but they're allowed by physics, and they could solve the problem of how black holes grew so large so quickly. The little red dots raise another question. Where did they go? These objects appear commonly when the universe is between a few 100 million and about 1 billion years old. But after that, they seem to vanish. We don't see similar objects in the universe today. What happened to them? The most likely explanation is that they evolved. As these young black holes continued accreting matter, they eventually consumed or dispersed their gas cocoons. Without the dense envelope, they would appear different. They might look like normal quasars, the extremely bright active galactic nuclei we see throughout the universe. Or they might have quieted down entirely, becoming the dormant supermassive black holes we find at the centers of most large galaxies today. This would make the little red dots a crucial phase in black hole evolution, a brief but important stage when young black holes are growing rapidly, shrouded in gas, transforming from intermediate mass black holes into the supermassive behemoths that dominate galactic centers. If this interpretation is correct, then the little red dots are giving us a window into how supermassive black holes formed. This is one of the great unsolved questions in astrophysics. We know that nearly every large galaxy contains a supermassive black hole at its center. The Milky Way has one, Sagittarius A, with a mass of about 4 million suns. But how did these objects form? How did they grow so large? The little red dots might be showing us the answer. But there's a deeper question here about the physics of black hole growth. The Eddington limit isn't just a suggestion. It's the fundamental consequence of how radiation pressure works. When matter falls into a black hole, it doesn't fall straight in. It forms an accretion disk, a swirling disk of gas spiraling inward. Friction in the disk heats the gas to millions of degrees. At these temperatures, the gas radiates intensely, primarily in X-rays and ultraviolet light. This radiation creates outward pressure on the surrounding gas. If the black hole tries to swallow matter too quickly, the radiation pressure becomes so strong that it pushes the infalling gas away. This is the Eddington limit. For a black hole to exceed this limit, something unusual must happen. One possibility is super-Eddington accretion through thick disks. If the accretion disk is very dense and geometrically thick, the radiation might be trapped inside the disk, allowing more matter to fall in. Another possibility is that the black holes are spinning rapidly. A spinning black hole drags space-time around with it, a phenomenon called frame dragging. This can affect how efficiently the accretion disk radiates, potentially allowing faster growth. Or perhaps the early universe provided conditions that simply don't exist today. In a denser, more compact universe, gas clouds might have been able to funnel matter into black holes more efficiently. The dynamics of galaxy mergers in the early universe might have driven gas towards central black holes at extraordinary rates. These are active areas of research. Astronomers are using Webb to study the properties of early black holes in detail, measuring their masses, their accretion rates, the properties of the gas surrounding them. Each observation adds another piece to the puzzle. But the sheer number of massive black holes Webb has found suggests something systematic is going on. It's not just a few lucky black holes that happen to grow unusually fast. It's a whole population of them, as if the early universe was optimized for rapid black hole formation and growth. This brings us back to the central question. Was it optimized by random chance, by conditions that just happened to favor black hole growth? Or was it seeded with structure from a previous universe, giving black holes a head start? Let's return to cosmic reionization. This is one of the major epochs in the history of the universe, and Webb's observations are forcing us to completely rethink what happened. After the cosmic microwave background was emitted, about 380,000 years after the Big Bang, the universe entered a period called the Cosmic Dark Ages. No stars had formed yet. The universe was filled with neutral hydrogen gas, cold and dark. Light from the cosmic microwave background could travel through this gas, but no new light was being produced. This period lasted for tens or hundreds of millions of years. Eventually, the first stars began to form. These were massive, hot, short-lived stars made purely of hydrogen and helium. When they ignited, they produced enormous amounts of ultraviolet radiation. This radiation had enough energy to ionize hydrogen, stripping electrons from hydrogen atoms. Around each star, a bubble of ionized gas began to grow. As more stars formed, more bubbles appeared and expanded. Eventually, these bubbles merged, and the entire universe transitioned from neutral to ionized. This process is called cosmic reionization. The universe was probably fully reionized by about 1 billion years after the Big Bang. But Webb is finding evidence that reionization might have happened differently. In early 2025, Webb observed a galaxy called JADES GSZ 131 LA. The spectroscopic redshift confirmed it existed just 330 million years after the Big Bang. This galaxy was emitting enormous amounts of ultraviolet radiation, and, crucially, it showed a clear Lyman alpha emission line. Lyman alpha is light emitted when hydrogen electrons drop from the second energy level to the ground state. It's one of the brightest emission lines in star-forming galaxies. But Lyman alpha light shouldn't escape from galaxies during the epoch of reionization. Here's why. Lyman alpha photons are easily absorbed by neutral hydrogen. If a galaxy is surrounded by neutral hydrogen gas, the Lyman alpha light gets absorbed before it can reach us. We shouldn't see it. Only after the universe is substantially ionized can Lyman alpha light travel freely through space. That's why finding strong Lyman alpha emission from a galaxy at redshift 13 was shocking. Kevin Heinlein, one of the researchers, stated they shouldn't have found a galaxy like this at all. The emission was entirely unexpected. Eurus Whitstock from the University of Cambridge described the result as entirely unexpected, with a remarkably strong and clear signature. The galaxy had carved out an ionized bubble of gas stretching 650,000 light-years in every direction. This is enormous. It means the galaxy's ultraviolet radiation had ionized a huge region of the surrounding intergalactic medium. But how? Either cosmic reionization began much earlier than models predict, or it happened much faster, or individual galaxies were far more effective at ionizing their surroundings than we thought. The power source is also unclear. Was it superhot stars producing the ultraviolet radiation? Or does this galaxy host an active supermassive black hole at its center? Black holes accreting matter produce intense radiation across all wavelengths, including ultraviolet. If this galaxy contains an already massive black hole, just 330 million years after the Big Bang, that raises the same problem we saw with the little red dots. Supermassive black holes take time to grow. They start as stellar mass black holes, perhaps 10 to 100 times the mass of the Sun. They grow by accreting gas or by merging with other black holes. Growing from stellar mass to supermassive, millions or billions of solar masses, requires either a very long time or extremely efficient accretion. There hasn't been much time by redshift 13, yet Webb keeps finding evidence of massive black holes in the early universe. Galaxies that appear to host black holes far larger than standard models allow. What does all of this mean? Webb has now been operating for over 3 years. In that time, it's revealed an early universe, far more active, far more structured, far more chemically evolved than anyone predicted. Massive galaxies appeared earlier than they should have. Black holes grew larger than they should have. Heavy elements showed up faster than they should have. Cosmic reionization might have started sooner and proceeded faster than models predicted. And the expansion rate doesn't match what our best theories calculate from the conditions of the early universe. None of this proves Penrose's cyclic cosmology. His Hawking points remain controversial, and most physicists don't accept them as real signals. But the accumulation of anomalies suggests something fundamental might be missing from our understanding. Maybe it's just that our models of structure formation are too simple. Maybe dark matter behaves differently on small scales than we thought. Maybe there are feedback processes we don't understand that accelerate galaxy formation and black hole growth. Or maybe the story is stranger. Maybe the Big Bang really wasn't the beginning. Maybe our universe inherited structure from something that came before. Let's explore what Penrose's theory actually claims about the transition between aeons. This is where the mathematics gets truly fascinating. In Penrose's conformal cyclic cosmology, the key insight is about scale. At the beginning of our universe, at the Big Bang, everything was compressed to an incredibly small size. But scale is meaningful only when you have something to measure against. At the very instant of the Big Bang, before anything existed to provide a reference, the concept of size was undefined. Similarly, at the end of a universe, after all, matter has decayed into massless particles like photons. Scale, again, loses meaning. A photon doesn't experience time or space in the way we do. From a photon's perspective, it's emitted and absorbed in the same instant, even if from our perspective, it travels for billions of years. When the entire universe consists of nothing but photons, there's no clock, no ruler, no way to measure distance or duration. Penrose realized that these two states, the infinitely compressed beginning and the infinitely diluted end, are mathematically equivalent under a conformal transformation. A conformal transformation is a way of rescaling space-time that preserves angles but not distances. Imagine stretching or compressing space and time by different amounts, but in a coordinated way, so that the geometric relationships between angles stay the same. If you apply the right conformal transformation to the infinite future of an old universe, it maps onto the Big Bang of a new universe. The transition is smooth. No singularity, no moment where physics breaks down. Just a continuous evolution from one eon to the next. This requires something specific to happen at the end of each eon. All massive particles must decay or be absorbed into black holes, which themselves eventually evaporate. This is where Penrose's theory requires physics beyond the standard model. In the standard model, protons are stable. They don't decay. Electrons are also stable. But in many extensions of the standard model, protons do eventually decay, given enough time. The current experimental limit on proton decay is something like 10 to the 34 years. If protons decay on timescales of 10 to the 40 years or 10 to the 50 years, we'd never detect it in the lab, but given cosmological timescales, all protons would eventually vanish. Similarly, electrons might lose their mass through some process we don't yet understand. Or they might combine with positrons in the far future, when the universe is so dilute that matter-antimatter pairs can find each other. The key point is that for Penrose's model to work, the end state of each aeon must be dominated by massless particles. Only then can the conformal transformation map the infinite future onto a finite Big Bang. There's another crucial element in Penrose's theory called the Weyl curvature hypothesis. This is about entropy and the structure of space-time. Curvature in general relativity comes in two types: Ricci curvature and Weyl curvature. Ricci curvature is associated with the presence of matter and energy. It's what causes space-time to curve around massive objects. Weyl curvature, different. It represents tidal forces, the stretching and squashing of space-time itself. Penrose argues that gravitational entropy is associated with Weyl curvature, not Ricci curvature. At the Big Bang, the Weyl curvature was essentially zero. The universe began in a state of very low gravitational entropy. As the universe evolves, structures form, black holes grow, the Weyl curvature increases. By the end of an aeon, when supermassive black holes dominate and then evaporate, the Weyl curvature peaks and then decreases again. At the transition to the next eon, the Weyl curvature returns to zero. This is how each cycle resets. The conformal smoothness at the end of one aeon naturally produces the low entropy beginning of the next. No fine-tuning, no special initial conditions, just the mathematics of conformal geometry carrying the universe from one cycle to the next. Critics have raised several objections to this picture. First, the requirement that all massive particles decay is not part of established physics. We have no evidence that electrons decay or lose their mass. Second, even if particles do decay, the process of black hole evaporation is incredibly slow for supermassive black holes. A black hole with 1 billion solar masses would take something like 10 to the 100 years to evaporate completely. That's far longer than the current age of the universe. For all the black holes in a universe to evaporate, you'd need to wait an unimaginable amount of time. Penrose's model requires that this waiting happens, that the universe expands and dilutes for an effectively infinite time before the transition to the next eon. Third, there's the information paradox. Black holes that evaporate should, according to quantum mechanics, release all the information they swallowed. But in Penrose's model, black holes evaporate across the boundary between eons. What happens to that information? Is it lost, violating quantum mechanics? Or is it somehow carried forward into the next universe? Penrose has proposed that quantum information might be preserved through the transition, that the Hawking radiation from evaporating black holes carries information forward as subtle correlations in the next universe's cosmic microwave background. But this is speculative. We don't have a quantum theory of gravity to tell us what really happens. Fourth, there's the question of thermodynamics. The second law says entropy always increases. Each aeon should have higher total entropy than the last. But Penrose argues that the conformal transformation resets gravitational entropy. The Weyl curvature goes to zero. The universe begins again with low gravitational entropy, even though the total entropy might still be increasing in some abstract sense across the full sequence of aeons. This is mathematically possible, but it's subtle, and not everyone finds it convincing. Despite these objections, the theory has appeal. It explains why the universe began in such a special state. It potentially explains features in the cosmic microwave background, if the Hawking points or similar signatures can be confirmed. But Penrose's conformal cyclic cosmology isn't the only alternative to the standard single Big Bang model. Over the past 2 decades, several other bounce cosmologies have been developed. The ekpyrotic universe, proposed by physicists Paul Steinhardt and Neil Turok in 2001, offers a radically different picture. In this model, our universe exists on a 4-dimensional membrane, a brain, floating in higher dimensional space. Every so often, our brain collides with another parallel brain. These collisions are what we experience as Big Bangs. Between collisions, the brains slowly move apart, pushed by a force that manifests as dark energy. After countless billions of years, the force reverses, the brains move back together, and they collide again. The collision releases enormous energy, creating a new, hot, dense state. Crucially, the approaching brains never reach infinite density. The collision is violent but finite, avoiding the mathematical breakdown that plagues standard Big Bang models. Another approach comes from loop quantum gravity. In loop quantum cosmology, space itself is quantized, made of discrete units. When you compress the universe toward the Big Bang, quantum effects prevent reaching a true singularity. Instead, the universe bounces. At extremely high densities, quantum gravitational repulsion halts the collapse and reverses it into expansion. This is called a big bounce. All bounce models share something important. They eliminate the need for an absolute beginning. Time extends infinitely into the past through cycles of expansion and contraction. But they also face the entropy challenge, just like Penrose's model does. Different bounce cosmologies handle it in different ways. What's fascinating is how these different approaches, Penrose's conformal geometry, Steinhardt and Turok's colliding brains, loop quantum gravity bounces, all arrive at similar conclusions from completely different starting points. The Big Bang might not have been a beginning. It might have been a transition, a bounce, a collision, a conformal mapping. What makes Webb's discoveries particularly intriguing is how they might connect to these ideas. If the early universe inherited structure from a previous eon, or cycle, that could explain the rapid formation of massive galaxies. It could explain black holes that grew too large too quickly. It could explain heavy elements appearing earlier than standard models. Think about what inheritance from a previous universe might look like. Penrose argues, Hawking radiation from evaporating black holes carries information forward. In ekpyrotic models, density fluctuations from the previous cycle might survive the brane collision. In loop quantum cosmology, certain quantum correlations could persist through the bounce. Any of these mechanisms could seed the next universe with patterns that accelerate structure formation. This isn't just abstract theory. It has observable consequences. If our universe inherited structure, the cosmic microwave background should show anomalies, not the smooth, nearly random pattern that inflation predicts, but subtle correlations. Patterns that can't be explained by quantum fluctuations alone. Some researchers claim they've found such anomalies. The so-called axis of evil, a preferred direction in space that shouldn't exist in a perfectly uniform universe. The cold spot, an unusually large region of lower temperature, low multipole suppressions, meaning large-scale patterns are weaker than expected. These anomalies are controversial. They could be real signatures of pre-Big Bang physics, or they could be statistical flukes, instrumental effects, or foreground contamination. But, if they're real, they might be telling us the Big Bang wasn't the beginning. There's another aspect of these theories worth exploring. The arrow of time. Why does time flow in one direction? Why do we remember the past, but not the future? Why do eggs break, but never spontaneously reassemble? These questions are connected to entropy. The second law of thermodynamics says entropy increases toward the future. The arrow of time points in the direction of increasing entropy. But this raises a puzzle. If the laws of physics are time-symmetric, if they work equally well forward or backward in time, why does entropy increase in one direction? The answer, in standard cosmology, is that the universe started with very low entropy. The Big Bang was an extraordinarily ordered state. Everything since has been entropy increasing toward disorder. But this just pushes the question back. Why did the universe start with low entropy? This is one of the deepest mysteries in cosmology. It's not just a technical question. It's a question about the fundamental nature of time itself. Cyclic cosmologies offer a potential answer. If the universe resets at each cycle, entropy can start low again without requiring special initial conditions. The conformal transformation in Penrose's model maps a high entropy end state to a low entropy beginning. The first bounce-in loop, quantum cosmology might erase entropy through quantum effects. The brane collision in ekpyrotic models could reset the entropy counter. This is philosophically attractive. It explains the arrow of time without invoking miraculous initial conditions. But it also raises new questions. If entropy resets, does causality survive across cycles? Can information pass from one aeon to the next? Or is each cycle truly independent, with no memory of what came before? Penrose argues, information does survive, encoded in the Hawking radiation. Others argue the transition erases almost everything. These aren't just academic questions. They touch on fundamental issues about the nature of time, causality, and existence. If our universe inherited structure from a previous eon, then the past extends infinitely far back. There was never a moment of creation ex nihilo, from nothing. Time has always existed. The cosmos has always existed. What we call the Big Bang was just a transition point, a reset, a new chapter beginning. This changes everything about how we think about cosmological history. It means the patterns we see in the cosmic microwave background might encode information from an unimaginably distant past. Information that survived the death and rebirth of an entire universe. It means the galaxies Webb observes might have been seeded by density fluctuations that originated trillions upon trillions of years ago in a previous aeon. It means our existence is connected to an eternal chain of cosmic evolution, stretching infinitely into the past and infinitely into the past future. It offers a framework for thinking about the universe as eternal rather than having a singular beginning. And now, with Webb's discoveries, it might offer an explanation for why the early universe looks so different from what we expected. If our universe inherited structure, patterns, maybe even entire objects from a previous aeon, that could explain the rapid formation of massive galaxies. It could explain the early presence of heavy elements. It could explain black holes that are too large, too soon. Think about what this means in concrete terms. In Penrose's model, the supermassive black holes that dominated the previous universe evaporated over incomprehensible timescales. Their final Hawking radiation was emitted as that universe expanded toward colonent infinity. This radiation got scrambled, diluted, spread across all of space, but it carried information, patterns, correlations. When the conformal transformation occurred, mapping the infinite future of the old universe onto the Big Bang of our universe, those patterns came with it. They showed up as subtle variations in the density of matter and energy in the early moments of our universe. These variations were amplified during inflation or during the early expansion. They seeded the formation of structure, leading to faster galaxy formation than would have occurred starting from purely random quantum fluctuations. This is speculative. Penrose hasn't worked out all the details, but it's a possibility that Webb's discoveries make worth considering. Let's talk about one more Webb discovery that adds to the mystery. In early 2025, researchers announced the discovery of the Big Wheel galaxy. This object exists within the first 2 billion years after the Big Bang. It's a huge spiral galaxy with beautiful, well-defined spiral arms. This is surprising because galaxies this early should be chaotic. They should be growing through violent mergers, collisions that would disrupt any delicate spiral structure. Spiral galaxies like the Milky Way are thought to form later, after things have settled down, after multiple generations of mergers have played out. Yet here's the Big Wheel, with pristine spiral arms, existing when the universe was only 15% of its current age. Either it formed through exceptionally smooth accretion, avoiding major mergers, or it experienced mergers but somehow preserved its structure through them. Both possibilities are unusual. Simulations of galaxy formation suggest that mergers almost always disrupt spiral structure, at least temporarily. Over time, the galaxy can settle back into a spiral configuration, but this takes hundreds of millions of years. The Big Wheel seems to have either avoided this process or recovered from it much faster than models predict. This is yet another piece of evidence that galaxy formation in the early universe doesn't follow the script we've written. There's one more aspect worth exploring before we step back to see the bigger picture: the nature of space-time at extreme scales and what it tells us about cosmic origins. When we observe galaxies at high redshift, we're probing conditions radically different from today. Understanding redshift is crucial. It's how we measure cosmic distances and look back in time. When light travels through expanding space, its wavelength stretches. The amount of stretching tells us how much the universe has expanded since that light was emitted. A galaxy at redshift 13 means the universe is 14 times larger now than when that light began its journey. This has profound implications. The galaxies Webb observes existed in a fundamentally different universe. Smaller, denser, hotter. In such conditions, gravity operates more strongly. Dark matter halos collapse faster. Gas clouds fragment more efficiently. Maybe that's why structure formation proceeded faster than current models predict. But there's something deeper. Observations at extreme redshifts probe the limits of general relativity. Einstein's theory has been tested extensively in the solar system and through gravitational waves. But those are low-energy regimes compared to the early universe. At redshift 14, densities were incomprehensible. Quantum effects might become important. This is where quantum gravity enters. We don't have a complete theory yet. String theory and loop quantum gravity are candidates, but neither is fully developed. What we know is that quantum gravity should produce corrections to general relativity at extreme energies. These corrections might affect early universe evolution. They might alter structure formation rates. Webb's observations might be the first hints of quantum gravitational effects, not through exotic particles, but through subtle modifications to how gravity works at extreme scales. If quantum gravity is important in the early universe, that has implications for cyclic cosmologies. Penrose's model is classical, based on general relativity. But the transition between eons might require quantum gravity. The moment when the universe goes from infinitely dilute to the Big Bang might be where classical physics breaks down. Loop quantum cosmology already incorporates this. Ekpyrotic models invoke string theory. The next generation of cosmological models might need to fully integrate quantum gravity as a fundamental ingredient. This is frontier territory, where cosmology meets quantum gravity, meets observational astronomy, where Webb's discoveries might reveal not just how galaxies formed, but how space-time itself behaves under extreme conditions. So where does all of this leave us? The standard Big Bang model has been the foundation of cosmology for over half a century. It's been tested extensively and has passed nearly every test. It explains the cosmic microwave, background radiation with remarkable precision. It predicts the abundances of light elements, hydrogen, deuterium, helium, lithium, matching observations almost perfectly. It accounts for the large-scale structure of the universe, the cosmic web of galaxies, clusters, and voids. It's a magnificent achievement of human understanding. But Webb is revealing cracks in the foundation. Not fatal flaws, not obvious contradictions, but persistent anomalies that suggest the picture is incomplete. The early universe was different from what we predicted. More active, more structured, more evolved. And the expansion rate doesn't match, no matter how carefully we measure it. These problems might be solved within the framework of the standard model. Perhaps we just need to refine our understanding of star formation efficiency or dark matter behavior. or the details of cosmic reionization. Perhaps the Hubble tension will be resolved when we get better measurements, or when we discover some subtle systematic error we've been overlooking. Or perhaps we need to think bigger. Perhaps the Standard Model, for all its successes, is missing something fundamental about the nature of cosmic origins. Perhaps the Big Bang wasn't the beginning, but a transition. Perhaps our universe is part of a larger multiverse, with interactions that affect structure, formation, and expansion. Perhaps Penrose is right, and the universe cycles through infinite eons, each one seeding the next. It's worth distinguishing between different types of multiverse theories. Some versions of inflation theory predict eternal inflation, where the inflating region never completely stops. Instead, inflation ends in some regions, creating pocket universes like ours, while continuing forever in other regions. This creates an infinite number of universes, each potentially with different physical laws and constants. In this multiverse, everything that can happen does happen, somewhere. There are universes where the electron mass is slightly different, where the cosmological constant is larger, where the laws of physics don't permit atoms to form. Most of these universes are sterile, unable to support complexity or life. We exist in one of the rare pockets where conditions happen to be right. This is called the anthropic principle. We observe a universe compatible with life, because we couldn't exist in any other kind. But many physicists find this deeply unsatisfying. It seems to give up on explaining why our universe has the properties it does. Instead of deriving the constants of nature from fundamental theory, we're told they're accidents of which pocket universe we happen to inhabit. Penrose's cyclic model is different. There's only one universe, cycling through different states. The laws of physics don't change between eons. The constants of nature remain the same. What changes is the structure, the distribution of matter and energy, the phase of the cosmic cycle. This is more philosophically appealing to those who want a deterministic, predictable cosmos. The ekpyrotic and loop quantum cosmology models fall somewhere in between. They avoid the singularity of the Big Bang through different mechanisms. But whether they produce one universe or many depends on the details of the theory. What all these alternatives share is a rejection of the idea that existence began at a singular moment. They push the question back. Instead of asking what caused the Big Bang, we ask what caused the previous bounce, or the previous collision, or the previous aeon. But this isn't circular reasoning. It's accepting that the question, what came first, might not have an answer. That time might not have a beginning any. More than a circle has a starting point. This is counterintuitive for human minds. We're used to things having beginnings. Stories have opening chapters. Lives have birth, moments. Projects have start dates. But perhaps the universe isn't like that. Perhaps it's more like a circle, or a cycle, or a wave that's always been oscillating. Physics doesn't require a beginning. The equations of general relativity work just as well with an eternal universe as with a created one. It's our intuition, our narrative-building minds, that insist everything must start somewhere. But the universe doesn't care about our intuitions. It is what it is, regardless of whether it fits our mental categories. This brings us to a crucial point about how science works. Paradigm shifts don't happen because of single observations. They happen when evidence accumulates to the point where the old framework can't accommodate it anymore. The shift from geocentric to heliocentric cosmology didn't happen because of one observation. It happened after decades of mounting evidence that the Earth-centered model required increasingly complicated epicycles to explain planetary motion. Eventually, the heliocentric model became simpler and more elegant. The shift from Newtonian gravity to general relativity happened the same way. Newtonian gravity worked perfectly for most applications, but anomalies accumulated. The precession of Mercury's orbit couldn't be explained. Light bending around the sun during eclipses didn't match predictions. Eventually, Einstein's theory provided a simpler, more comprehensive framework. We might be at the beginning of a similar shift in cosmology. The standard Big Bang model with inflation works remarkably well. It explains the cosmic microwave, background, light element abundances, large-scale structure. But cracks are appearing. The Hubble tension won't go away. Webb keeps finding galaxies and black holes that formed too early. Cosmic microwave background. Anomalies persist. Maybe these are just details to be worked out within the existing framework. Or maybe they're the first signs that the framework itself needs replacing. History suggests we should keep an open mind. The greatest scientific breakthroughs often come from questioning the most fundamental assumptions. And few assumptions are more fundamental than whether the universe had a beginning. When Penrose proposed conformal cyclic cosmology, most physicists dismissed it. Too speculative, too dependent on physics we don't understand, too difficult to test. But he persisted. He searched for observational signatures. He refined the mathematical framework. He published papers, gave talks, defended his ideas. Now, more than a decade later, the theory hasn't been confirmed, but it also hasn't been definitively ruled out, and Webb's discoveries have made it slightly more plausible than it was before. That's how science progresses. Not through sudden revolutions where yesterday's certainties become today's errors, but through gradual accumulation of evidence, shifting probabilities, evolving understanding. Ideas that seemed crazy become respectable. Respectable ideas become mainstream. Mainstream ideas become textbook facts. And sometimes, textbook facts turn out to be approximations of something deeper and stranger. That might be happening now with the Big Bang. For 50 years, it's been a textbook fact. The universe began 13.8 billion years ago. Before that, nothing. But maybe that fact is an approximation. Maybe the fuller truth is that the Big Bang was a transition in an eternal cosmos. Maybe we're one aeon in an infinite sequence. Maybe. Death and rebirth happen on the largest scales, just as they do in every other domain of existence. Let's think about what it would mean if Penrose's model turned out to be correct. Every atom in your body would be part of an eternal cycle. The hydrogen in your cells wasn't just created in the Big Bang. It's been through countless previous Big Bangs, countless previous universes. The patterns of galaxies across the sky would echo patterns from previous eons. Faint correlations in the cosmic microwave background would be fingerprints of supermassive black holes that evaporated in a universe that ended trillions upon trillions of years ago. Death and rebirth on the largest possible scale. The universe expanding, cooling, stars forming and dying, galaxies merging and drifting apart, black holes growing and eventually evaporating. The expansion continues until everything is diluted into a thin soup of photons and maybe other massless particles. Matter has decayed. Only energy remains. And in that state, time becomes meaningless. A photon doesn't experience time. From a photon's perspective, there is no duration. It exists in an eternal now, when the entire universe consists of nothing but photons. Scale also becomes meaningless. There's nothing to measure against. A universe stretched to infinite size is mathematically equivalent to a universe compressed to a point. This is the essence of conformal geometry. You can map one state onto the other. The infinite future of the old universe becomes the Big Bang of the new one. The transition is smooth, continuous. No singularity, no moment where physics breaks down, just a conformal transformation connecting two eons. But what would this feel like if you could somehow experience it? Of course, you couldn't. By the time a universe reaches its end state, all stars have died, all planets have been destroyed or scattered into interstellar space. All life has long since ceased. Nothing remains but photons racing through an ever-expanding void. But imagine if you could observe from outside, in some higher dimension. You'd see a universe that started dense and hot, filled with particles and radiation. Expansion would begin, space stretching, temperature dropping. Stars would form, galaxies would appear. Structure would emerge from chaos. For billions of years, perhaps trillions, the universe would be vibrant, active, full of light and motion. But gradually, things would slow down. Stars would exhaust their fuel. New star formation would cease as available gas was used up or dispersed. Galaxies would drift apart, carried by the expansion of space, until each galaxy was alone in an ever-darkening void. Within each galaxy, stars would continue to die, white dwarfs would cool. Neutron stars would radiate away their heat. Black holes would dominate. Eventually, even the black holes would evaporate, releasing their mass as Hawking radiation over timescales so long that calling them astronomical would be an absurd understatement. The universe would be empty, dark, cold. Space would continue expanding, but there would be nothing in it except occasional photons, stretched to wavelengths longer than the size of galaxies. And then the transition. From your perspective outside, you'd see the infinite expansion somehow fold back on itself. The dilute, empty end state would transform into a compressed, hot beginning, not through contraction, not through a reversal of expansion, but through a mathematical mapping that makes the two states equivalent. And then it would begin again. A new eon, a new universe, dense, hot, filled with energy. Inflation, or its equivalent, would smooth out irregularities. Particles would form from pure energy. Nucleosynthesis would create light elements. The cosmic microwave background would be emitted, and the cycle would continue. Whether this is actually what happens, we don't know. Penrose's model is one possibility among several. It's mathematically elegant. It solves certain problems, like the low entropy initial conditions of the Big Bang. But it requires physics we haven't confirmed, like the eventual decay of all massive particles. And it makes predictions, like the Hawking points, that remain controversial and unconfirmed. What we do know is that the universe revealed by Webb is different from what we expected. And when observations diverge from theory, that's when science gets interesting. That's when we have the opportunity to learn something genuinely new. The next few years will be crucial. Webb will continue observing, pushing even deeper into the early universe. The Nancy Grace Roman Space Telescope is scheduled to launch, probably in late 2026. Roman will have a field of view 100 times larger than Webb's. Where Webb gives us deep, detailed views of small patches of sky, Roman will survey enormous areas. This will tell us whether the early massive galaxies Webb has found are rare anomalies or common features of the early universe. If they're rare, maybe they're just statistical flukes. unusual regions where galaxy formation happened faster than average. If they're common, that's a much bigger problem for standard cosmology. The Euclid mission is also gathering data, mapping the large-scale structure of the universe with unprecedented precision. This will improve our understanding of dark matter and dark energy. It might resolve the Hubble tension, or it might deepen it. Ground-based observatories are being built that will complement Webb's observations. The extremely large telescope in Chile will have a 39-meter mirror. The 30-meter telescope, if it gets built, will rival it. These telescopes will be able to study the atmospheres of exoplanets in detail, but they'll also contribute to cosmology, measuring distances and expansion rates with increasing precision. Within 5 to 10 years, we should know whether the anomalies Webb has found represent a fundamental challenge to cosmology or just refinements to our models. We should know whether the Hubble tension requires new physics or can be explained within the standard model. We should know whether the early universe really was as different as current observations suggest. And if the problems persist, if the observations keep defying our models, then ideas like Penrose's cyclic cosmology will move from fringe speculation to mainstream consideration. Not because they're proven, but because they offer frameworks for understanding a universe that turns out to be stranger than we imagined. There's something profound about questioning whether the Big Bang was the beginning. It's such a fundamental assumption in modern cosmology that challenging it feels almost heretical. We've become accustomed to thinking of the Big Bang as the moment of creation, the origin of space and time. Before the Big Bang, there was nothing. No space, no time, no matter, no energy, just nothing. The universe began 13.8 billion years ago, and before that, the concept of before doesn't even make sense. This is what we've been teaching for decades. But what if it's wrong? What if the Big Bang was just a transition, an event, not the event? What if the universe is far older than 13.8 billion years? Older than we can possibly measure because it's been cycling through eons for eternity. This changes everything. It changes how we think about origins, about existence, about the nature of time itself. An eternal universe has no beginning and no end. It just is. Always has been, always will be. Transforming, evolving, cycling, but never truly beginning or ending. This is both humbling and awe-inspiring. Humbling because it makes our universe, already vast beyond comprehension, just one chapter in an infinite book. Our 13.8 billion years of history becomes a fleeting moment in an endless story. Awe-inspiring because it suggests existence itself is eternal. That reality has always existed in some form and always will. That the cycle of creation and destruction, birth and death, is fundamental to the nature of the cosmos. Let's consider what this means for humanity's place in the universe. For most of human history, we believed Earth was the center of everything. Then we learned we orbit the sun. Then we learned the sun isn't the center of the galaxy. Then we learned the galaxy isn't the center of the universe. There is no center. We're on an ordinary planet, orbiting an ordinary star in an ordinary galaxy. This is called the Copernican principle. Now we might be facing another shift, not about our location in space, but our location in time. If the Big Bang was the beginning, we exist in a universe that's 13.8 billion years old. We live in a brief era when stars shine and planets exist and life is possible. But if the universe is cyclic, if it's been going through eons forever, then our era isn't special. It's just one moment in an infinite sequence. Other universes came before ours. Other universes will come after. We're not living in the Prites universe. We're living in a universe. One iteration of an eternal cycle. This is both humbling and awe-inspiring in new ways. Humbling because it makes our existence even more temporary. Not just temporary within a universe that will eventually die, but temporary within an infinite sequence of universes. Awe-inspiring because it suggests existence itself is fundamental and eternal. That the cosmos doesn't need creation, doesn't need a first cause. It simply is, always has been, always will be. This connects to ancient philosophical and religious ideas. The Hindu concept of cosmic cycles, yugas stretching across vast time periods. The Buddhist idea of endless rebirths, samsara, without beginning or end. The Stoic concept of eternal recurrence, the cosmos going through infinite cycles of conflagration and renewal. These ideas have existed for millennia. Now, they're being explored through physics and mathematics, ancient wisdom, and cutting-edge science converging on similar conclusions. The universe might be eternal. Time might have no beginning. What we call creation might be transformation. Think about the timescales involved. If the universe really is cyclic, each aeon might last an almost incomprehensible amount of time. Our current aeon has been expanding for 13.8 billion years. If it continues expanding forever, stars will burn out in trillions of years. Galaxies will drift apart in hundreds of trillions of years. Black holes will evaporate in 10 to the 100 years. The transition to the next aeon, if it happens, is unimaginably far in the future. Compared to those timescales, human civilization is a blink. Recorded history is about 5,000 years. Modern science is a few hundred years old. We exist in a brief instant in the early stages of one aeon of possibly infinite eons. This perspective should inform how we think about meaning and purpose. What we do matters to us, to our descendants, to life on Earth. But on cosmic scales, our existence barely registers. This could be depressing. If we're so insignificant, why does anything matter? But it could also be liberating. Free from the burden of cosmic importance, we can focus on what actually matters to us, making life better for ourselves and others, exploring the universe because it's fascinating, creating art and music and literature because it brings joy. The universe doesn't need us to have a purpose. We create our own purpose through our choices and actions. And one of those purposes, for some of us, is understanding where we came from, understanding the nature of reality, pushing the boundaries of human knowledge as far as they'll go. The next decade will be crucial for testing these ideas. Webb will continue observing, going even deeper, finding even earlier galaxies. Each new observation either confirms or challenges our models. The Nancy Grace Roman Space Telescope should launch in late 2026 with its wide field of view. It will survey vast areas of sky, where Webb gives us deep, detailed looks at small regions. Roman will tell us how common these early massive galaxies really are. The Vera Rubin Observatory will conduct the Legacy Survey of Space and Time, 10 years of observations, creating the most comprehensive map of the universe ever made. Billions of galaxies, tracked over time, revealing how structure evolved. Ground-based, extremely large telescopes are under construction. The Extremely Large Telescope in Chile, with its 39-meter mirror. These will complement Webb's observations with different capabilities. They'll study the earliest quasars and black holes. They'll probe the dark ages of the universe, the era before the first stars formed. New gravitational wave detectors are coming online. LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from supermassive black hole mergers. These mergers happen throughout cosmic history. LISA will hear the echoes of black holes colliding billions of years ago. If Penrose is right about black hole evaporation, carrying information across eons, gravitational wave astronomy might provide clues. The cosmic microwave background will be studied with ever greater precision. New satellites and ground-based experiments will map polarization in exquisite detail. The search for primordial gravitational waves continues. If they're detected, they could distinguish between inflation and alternative models. All of these observations will constrain the possibilities. They'll rule out some models and lend support to others. The picture will become clearer, and sometime in the next 10 to 20 years, we might reach a consensus. Either the standard Big Bang model with modifications can explain everything, or we'll need something fundamentally different. Either way, we'll know more about where we came from than any previous generation. Penrose will turn 94 in August 2026. He's spent decades developing his conformal cyclic cosmology, refining the mathematics, searching for observational evidence, defending his ideas against skepticism from colleagues. He may not live to see his theory definitively proven or refuted, but he's accomplished something important, regardless of whether a specific model is correct. He's expanded the space of possibilities. He's shown that the Big Bang doesn't have to be the beginning, that there are mathematically rigorous alternatives to the standard story, that we can think about cosmic origins in fundamentally different ways. This is what great scientists do. They don't just solve problems within existing frameworks. They question the frameworks themselves. They ask, what if the assumptions we're making are wrong? They imagine alternatives that others dismiss as impossible. And sometimes, those alternatives turn out to be right. General relativity seemed absurd when Einstein first proposed it. Curved spacetime, time dilation, the equivalence of gravity and acceleration. Most physicists couldn't accept it. It took years and multiple experimental confirmations before the scientific community came around. Quantum mechanics faced similar resistance. Wave-particle duality, uncertainty, entanglement, the measurement problem. These ideas were so counterintuitive that even some of the theory's founders never fully accepted them. Yet quantum mechanics turned out to be correct, or at least an excellent approximation of reality. The expansion of the universe was ridiculed when first proposed. Steady-state cosmology dominated for decades, with many prominent astronomers arguing the universe was eternal and unchanging. The Big Bang model seemed absurd. The idea that the entire universe emerged from a singular point was too strange to take seriously, until the evidence became overwhelming, until the cosmic microwave background was discovered and steady-state cosmology collapsed. Now, maybe we're ready for another revolution. Maybe we're ready to question whether the Big Bang was really a beginning. Maybe Penrose's cyclic cosmology, or some variant of it, will be the next major shift in our understanding. Or maybe the multiverse interactions will prove to be real, and we'll discover that our universe is just one bubble in an infinite foam. Or maybe it's something else entirely. Something we haven't imagined yet. The beauty of science is that we don't have to guess. We can test ideas. We can make predictions and check them against observations. We can build better telescopes, gather more data, refine our models, and slowly, painstakingly, we can figure out what's actually true, not what we want to be true, not what seems philosophically appealing, but what the evidence tells us. That's the process. And right now, we're in the middle of it. Webb has given us data that challenges our models. We're trying to figure out what it means. Does it mean our models need tweaking? Does it mean we need new physics? Does it mean the whole framework of single-universe Big Bang cosmology is incomplete? We don't know yet, but we will. Maybe not this year, maybe not next year, but eventually. The telescopes will keep observing. The data will keep accumulating. The theorists will keep modeling. And eventually, a picture will emerge. Either the anomalies will be explained within the standard model, and we'll breathe a sigh of relief that our understanding was mostly correct. Or the anomalies will persist, will grow, will demand explanation. And then we'll know we need something new, something bigger, something stranger. Maybe Penrose's cycles, maybe multiverse interactions, maybe something no one has thought of yet. When you look up at the night sky tonight, think about what you're seeing. Light from stars that formed billions of years ago. Light from galaxies racing away from us as space itself expands. Light carrying information about the blood, history of the universe, about its structure, about its evolution. All of it telling a story we're still learning to read. For most of human history, we couldn't read that story at all. We saw stars, we saw planets, we told myths to explain them. Only in the last century have we developed the tools to understand what we're seeing, to measure distances to galaxies, to calculate the age of the universe, to map the cosmic microwave background. And only in the last few years have we been able to see deep enough into the past to observe the universe as it was in its infancy. What we're finding is that the infant universe was not what we expected. It was more mature, more developed, more active, as if it had a head start, as if something came before. Maybe that's just an illusion created by our incomplete models. Maybe once we understand star formation and black hole growth and cosmic reionization better, everything will make sense within the standard framework. Or maybe it's a genuine clue, a hint that the story we've been telling about cosmic origins is incomplete, that there's a chapter before the one we know. A previous universe, a previous aeon, something that seeded our universe with structure and patterns, and perhaps even objects that survived the transition. If that's true, if Penrose is right, or if something like his model is right, then the implications are staggering. It would mean the universe is eternal. Not eternal in the sense that it will last forever into the future, though it might, but eternal in the sense that it has always existed, stretching infinitely far into the past, each aeon giving birth to the next in an endless cycle. It would mean that death is not the end, even on cosmic scales, that every ending is a new beginning, that the universe itself undergoes a kind of reincarnation, dying and being reborn over and over again. It would mean that existence itself is fundamental, eternal, indestructible. The specific forms change, galaxies come and go, stars live and die, but existence itself persists forever. This is philosophy as much as physics. Questions about the nature of time, the meaning of existence, the ultimate fate of everything. These are questions humans have been asking for millennia. Now, finally, we have the tools to potentially answer them. Not with certainty, not with complete proof, but with evidence, with observations that constrain the possibilities, with mathematical models that make testable predictions. We can turn ancient philosophical questions into scientific ones. And that's extraordinary. It means that in our lifetimes, we might witness one of the greatest discoveries in human history. The discovery of what came before the Big Bang. The discovery that our universe is one in an infinite sequence. The discovery that existence itself is eternal. Or we might discover that the Big Bang really was the beginning, that the standard model is correct, that the anomalies were just misunderstandings. Either way, we'll know. We'll have pushed the boundaries of human knowledge to answer one of the deepest questions we can ask. Where did everything come from? So, as you go about your life, as you deal with the mundane concerns of daily existence, remember that you're living through an extraordinary time, a time when humanity is probing the deepest mysteries of the cosmos, a time when we're observing the universe as it was in its infancy and finding surprises that challenge everything we thought we knew, a time when ideas that seemed like science fiction or philosophy are becoming testable scientific hypotheses. The little red dots, the universe breakers, the rapid chemical enrichment, the Hubble tension, Penrose's Hawking points. All of these are pieces of a puzzle we're trying to solve, and the picture that emerges might be stranger and more beautiful than anything we imagined. An eternal cosmos, cycling through death and rebirth, each aeon giving rise to the next, an infinite sequence of universes, each one carrying forward subtle patterns from the one before. Death becoming birth, ending becoming beginning, an eternal dance of creation and destruction on the largest scale imaginable. Whether Penrose's specific model is correct doesn't really matter in the end. What matters is the willingness to question fundamental assumptions, to look at the data without preconceptions, to follow the evidence wherever it leads, even if it takes us to places that seem impossible. That's the spirit of scientific inquiry. That's what drives discovery. Not adherence to established models, but the courage to challenge them when the evidence demands it. Penrose has that courage. At 93 years old, having already won a Nobel Prize, having already made fundamental contributions to physics and mathematics, he continues to push ideas that most of his colleagues dismiss. He continues to search for evidence of a universe before ours. He continues to refine his mathematical framework. He continues to argue that the Big Bang wasn't the beginning. That's admirable. Whether he's ultimately proven right or wrong, the asking of the question, the serious scientific investigation of alternatives to the standard model, that's valuable in itself. Because it keeps us honest. It prevents us from becoming too comfortable with our current understanding. It forces us to keep testing, keep observing, keep thinking. And that's how science advances. Through creative tension between established models and new observations that don't quite fit. Through brilliant individuals willing to propose outrageous ideas and then do the hard work of testing them. Through the accumulation of evidence that slowly, incrementally, shifts our understanding of what's possible. The universe Webb is revealing is different from the one we predicted. More vibrant in its early stages, more structured, more chemically evolved. Whether this points towards cyclic cosmology, multiverse interactions, or just more efficient structure formation, we don't yet know. But the mystery is what makes it exciting. The not knowing. The possibility that everything we thought we understood might need revision. That's the frontier of knowledge. That's where discoveries happen, and we're fortunate to be alive at this moment, watching it unfold in real time. watching the most powerful telescope ever built peer into the early universe and find surprises. Watching physicists and astronomers grapple with observations that challenge fundamental assumptions. Watching humanity push the boundaries of what's knowable. This is what it means to be part of a scientific civilization. To ask questions about the nature of reality, and then actually try to answer them, not through speculation or faith, but through observation and measurement and rigorous mathematical modeling, to be unsatisfied with not knowing, and to build the tools needed to find out, to invest billions of dollars and decades of work into projects like the James Webb Space Telescope, solely because we want to understand where we came from. That's extraordinary. That's uniquely human. That capacity for wonder, for curiosity, for the relentless pursuit of understanding. So, when you look at the stars tonight, to feel that wonder, feel the weight of 13.8 billion years of cosmic history. Or maybe, if Penrose is right, feel the weight of infinite aeons, stretching infinitely far into the past. Feel the mystery of existence itself. Why is there something rather than nothing? Why do the laws of physics take the form they do? Why does the universe exist at all? We don't know the answers to these questions. We may never know, but we keep asking, we keep searching, we keep building better telescopes and developing better theories. We keep pushing against the boundaries of the unknown. And occasionally, very occasionally, we push through. We discover something genuinely new. We answer a question that's been asked for millennia. We expand human knowledge into territory that was previously inaccessible. That's what's at stake with the questions we've explored tonight. Did the Big Bang have a beginning? Or is the universe eternal, cycling through infinite eons? Are the anomalies Webb has found just quirks of our incomplete models? Or are they genuine hints of something stranger than we imagined? We don't know yet, but we will. And when we do, when the observations either confirm or refute Penrose's ideas, when the picture finally comes into focus, it will be one of those moments when human understanding takes a leap forward. When we answer a question we've been asking since we first looked up at the night sky and wondered where it all came from. Thank you for joining me on this journey through one of the most profound questions in cosmology. The discoveries from Webb are still coming. Every few weeks, new observations are announced. New galaxies, new anomalies, new mysteries to solve. The next decade will be extraordinary. It will reveal whether these early surprises point toward new physics, cyclic universes, or just refinements to our existing models. But whatever we discover, it will deepen our understanding of where we came from and what the universe truly is. Sleep well tonight, knowing that you're part of a cosmos that might be eternal, that the stars you see are part of an infinite story, that every ending, even the end of the entire universe, might be just another beginning, and that, right now, in this moment, humanity is closer than ever to understanding the deepest mystery of all, what came before the Big Bang, or whether there was a before at all.